Great. So now I'm going to, I'll talk a little bit, but I'm going to share my screen. Meanwhile, I want to talk a little while I get a blank screen here.
Hello, Professor. Can you hear me?
Yeah, I'm listening.
Okay, this is Dennis. My microphone wasn't working when you were doing attendance, but
Sorry.
this is Dennis. My microphone wasn't working when you were doing attendance, so you didn't hear what
Okay, just remind me later. I'm in a different screen now. Okay.
Okay.
Okay. Can you all see my screen?
Yes, Professor, we can see it.
Okay. So let me, all right. So I'll start class in a minute, just some general rules. I asked you to quickly, I asked you to look at sections 1 and 2 before the start of class. I'm going to go through those very quickly. Let me just talk a little bit about the class. This is a course in probability. The first few sections in the book, we don't really get into probability until chapter 2. But you need certain tools for probability. One of the languages that we use for probability is set theory. And sometimes you have to be able to count properly. So we need to do a little bit about permutations and combinations. So those are the key ideas that we're going to be talking about in the beginning. You won't need calculus until we get to chapter 3. And there we'll be doing integration and differentiation of various functions in studying the probability of these so-called continuous random variables. So we have a little bit of time before. There will be exams. The exams will be on campus. I will let you know what the room numbers are when they happen. So all exams will be in campus. You may need to scan things and send them to me. I'm making the assumption that all of you know how to create a PDF. That is, if I have a 4 or 5 page document, for example, like an exam, and I want you to send it to me, you would convert it to a single PDF oriented properly and send it to me. And I've given you instructions how to do it. You can just Google it as well. It's very easy to construct PDFs. I imagine most of you have done it already. Does anybody have any general questions before we begin? Okay. So I'm going to begin with set theory. And I'm going to move pretty damn fast, okay? So what is a set? A set is really nothing more than a well-defined collection of objects. I can give a formal definition. I don't really think it's necessary. At this point, this will be enough. And we usually designate a set by an uppercase letter, A, B, C, and so on. You can use any letter you really like, but we tend to use uppercase letters, capital letters, to represent a set. And if something belongs to a set, for example, here, let me describe a set. Set A is a counting number, say numbers 1 through 5. So what I do, here's one way of representing the set. I put curly brackets around it, and I indicate the elements of the set. To indicate that 1 is an element of the set, I could write 1 belongs to A. To indicate that 17 is not an element of the set, the line through it negates it, I could write it this way. So here's one way of representing a set. It's not the most efficient way. By the way, if you guys have questions along the way, just unmute yourself and ask them, okay? Here's another way of representing the same set. A is a set of all numbers x such that, the vertical line is read such that x is between 1 and 5, and x is an integer. So this is sometimes a simple way of representing a set. For example, instead of writing the numbers, I'll call this set A2, 1 to 1,000,000, I could just do this. It's a lot easier than writing everything out carefully. So we have different ways of representing a set. Now, what we need to do next is construct an algebra of sets, because we're going to have to be able to use this. So let me just proceed with an example. Well, let me give you a definition. I don't like the way this is the thickness here. Let's make this a little thinner. Oops, sorry. Apparently. Okay. Why is it coming out so thick? Okay. A is a subset of B. I don't know why my thing is.
You might want to use the dots on the, yep.
Yeah, okay. A is a subset of B if every element of A is in B. So I would, and the symbol for that would be A is a subset, or A is contained in B. Sometimes, instead of saying subset, some other books will say superset, and they would write it this way. B is a superset of A. It's sort of like an inequality symbol. So, for example, if A is the set with elements 1, 2, 3, and B is a set of elements 1, 2, 3, 4, then we see that A is a subset of B. This is the trivial example. So in a sense, if I drew a picture, if this represented the set A, then this would represent the set B. A is contained within B. Pictures like this sometimes have a name. Sometimes they're called the Venn diagram. We'll talk about these a little bit more very shortly. So question, true or false? True or false?
True.
True. Is every element of A and B? Yeah, so it's a subset. It's a trivial subset, by the way. Okay, so with this definition, I can define equality. A equals B if A is contained in B and B is contained in A. So that's what we mean by equality. Notice when you work with inequality, sometimes you use the symbols less than and less than or equal to. The symbol as I defined it can include the less than or equal to part if I wanted it to. Okay. Now, let's look at a trivial example. Suppose A is a set A1, A2, A3. So let's list all possible subsets. Well, here's one of them, right? That's one possible subset. Here are other possible subsets. Here's one. Here's one. Here's one. Right? Or A1 and A2. Or A1 and A3. Or A2 and A3. So the way I can get a subset is look at the original set and just delete some elements. In fact, there's one more subset here. This one. The set with no elements. This is called the empty set or the null set. In fact, I can prove it in words. Is there any element in this set that's not in A? And clearly the answer to that is no. Therefore, every element in the empty set is in A. In fact, there are none. In fact, more generally, given any set A, we have the empty set is a subset of that set. So make an observation here. The set A had 3 elements in it, A1, A2, and A3, and has a total of 1, 2, 3, 4, 5, 6, 7, 8 subsets. Anybody know why it's 8?
Wasn't there a thing that was like, for some reason it's 2 to the 3rd equals 8, and it's like 2 to the exponent of however many elements are in that set. That's how many subsets you have.
That's Anu. So,
Hi.
so my question, Anu, is why would it be 2?
There was like some number theory that I can't think of right this minute, but I know it's like 2 to the
Well,
number of.
I'll tell you
Yeah.
the answer now, but I don't know if you'll appreciate the answer until we get a couple of sections later. The answer is, if you look at every subset, each element has 2 possibilities. It's either in the subset or it's not in the subset. And when we learn about counting, the multiplication principle or the fundamental principle of counting, you'll see why there are 3 elements, we multiply 2 by itself 3 times. Similarly, if we had a set with 5 elements, there would be 2 to the 5th subsets. And by the way, the set of all subsets has a name as well. That's called a power set. The set of all subsets. Okay. So now that we have the notion of a set, we have the notion of containment, we want to develop an algebra of sets. Okay, let me just see what I want to do next. Okay, so very often, okay, well, so let me backtrack. So we have the notion of the empty set. So if you looked at the problem we did a minute ago, well, we had a total of 8 subsets of the set A, which had the elements A1, A2, and A3. Notice 6 of them are what we call proper subsets, namely not the null set and not the set itself. So we have the notion of a proper subset means any subset which is not either the set itself or the empty set. Now, in any discussion, the set A represents something. For example, suppose I'm talking about population studies. Well, I might talk about the set of all blonde-haired people. I may talk about all people between the ages of 14 and 27. I may talk about all left-handed people. So we have lots of different sets in the context of population studies. And there's one set that's generally bigger than every other set in the discussion. And that's called the universal set. Now, the universal set is usually obvious or given to you. For example, in the example I just considered, universal set would be the set of all living beings. So the universal set will represent by the letter U, and if A is any set, it will be a subset of the universal set. Now, sometimes you draw this pictorially. For example, if this is A, we have one really large set, which we call the universal set. So it's usually pretty obvious what the universal set is in the context of discussion, or if it's not obvious, it'll be given to you. So we have these 2 unusual sets, the empty set, and we have the universal set. The empty set, in the sense, is the smallest possible set. There's nothing in it. And the universe is the largest possible set. It has every element under the discussion in it. And every other set must be a subset of it. So now we're ready to develop an algebra of sets. And the first part of our algebra is we want to talk about the union of sets. So let me give you the definition. We write A union B, here's a symbol for union, is a set of all X such that X is an element of A or X is an element of B. Now, you got to be a little bit careful. I'm using the word or. And in the context of mathematics and usually in logic, the or is said to be inclusive. For example, if I'm saying I'm going to have ice cream or cake for dessert. That means either I'm having ice cream, or I'm having cake, or I'm having both. So if I wanted to represent this pictorially, I'll give you a numerical example in a second. Here's my universe. Here's A. Here's B. If I want to shade in the region in question, every element is either in A or in B or both. For example, if A was a set with elements 1, 2, 3, 4, 5, if it's a set 4, 5, 6, 7, then A union B would be 1, 2, 3, 4, 5, 6, 7. Every element is either in A or in B or in both. Okay? And by the way, notice if I had a set C, which is 1, 2, 3, I could just as well written it as 3, 2, 1. The order really doesn't matter. Normally, when you write the elements in the set, you want to do it in some logical way. And by the way, if D is the set 1, 1, 1, 1, this is really just a set which contains one element, 1. So I wouldn't repeat elements. So basically, to get the union, you take all of A, you take all of B, you throw them together into one set, and you don't list any element more than once. Okay. Anybody have any questions so far? Another way of saying the union of A and B consists of elements that are at least in one of the two sets. Next notion is the intersection. Again, a lot of this stuff you probably had in elementary school, but I want to be complete and I want to make sure we have it all because these are important for us. So we define the intersection written A intersection B as a set of all elements X such that X is an element of A and X is an element of B. Precisely those elements that are in both sets. Pictorially, here's A. Well, it's a funny circle, but it doesn't matter. Here's A, here's B. It's the region common to both. So in the example I had a moment ago, where A was, what was it? 1, 2, 3, 4, 5. B was 4, 5, 6, 7. The intersection would just be what they have in common, namely 5. Okay. I need 2 more ideas, and then maybe we'll do an example or 2, and then effectively we've considered the basic notions of sets that I'm going to need for probability, and then I want to talk a little bit more. Okay. The relative complement. Okay, I'm assuming, of course, I'm giving you the universe, okay? I wanted to find the relative complement. I'll say A minus B. Okay, and now I'm going to define this as follows. It's a set of all elements X such that X is an element of A and X is not, and X is not an element of B. Pictorially. I don't know why my circles aren't coming out circles, because I'm probably not.
Professor, is that A minus B, or am I reading that wrong?
A minus B.
Okay.
So here's A, here's B. A minus B would be all elements in A that are not in B. See it? In the example I considered above, I look at A, and I want the elements in A that are not in B. I get 1, 2, 3. Notice, by the way, B minus A would be 6 and 7. So essentially what you're doing, if you want A minus B, you look at A and you throw away the intersection. Or if you want B minus A, you look at B and you throw away the intersection. So each of these is called the relative complement. And now I want to define the complement. And by the way, in this example, let's assume the universe consists of the numbers 1 up to 10. Okay, I just defined that. So I'm going to define the relative complement. The symbol I use for the, the complement. The symbol I use in the text for the complement, which one do I use, is A prime. You'll see other books may use the symbol CA, A to the C. There are some books that write, well, very few use this one. Let me get rid of it. So I will be using the top symbol in the text. And my definition will be very simple. U minus A. That means you look at the universe and you throw away the elements A. So in the example above, if the universe consists of the numbers 1 through 10, and if I throw away A, well, A is 1, 2, 3, 4, 5. I'm left with 6, 7, 8, 9, 10. So the complement is essentially look at the universe and throw away the set A. And what you're left with is the complement. And the picture of this, of course, is if this is A, the complement is everything outside of A. Some words, A and B are said to be disjoint if they have nothing in common, and we can write that as what they have in common is the empty set. So sometimes we'll talk about disjoint sets. That just means they have nothing in common. Okay. Sometimes things get a little more complicated and we want to make sure we can understand them. So let's suppose I have 3 sets. Oops. Doesn't want to come out circular one more time, then we'll dump it. Okay, and the third one. Okay, and so let's suppose this is A, this is B, this is C. Notice this region right here. That would be A intersection B intersection C. How would I describe this region? Well, it's out of A, and it's in B, and it's in C. So I can describe that region pretty easily. How would I describe, say, this region by itself? Well, it's only in A, right? It's in A, and it's not in B, and it's not in C. So I can describe these regions fairly easily using Venn diagrams, and that's pretty useful. Some other remarks. Well, perhaps an example or two. Suppose I wanted to show that A intersection A complement intersection B complement equals A union B. This, by the way, is one of De Morgan's laws. I'll summarize it to later. Well, logically, why is this true? I mean, I can give you a logical reason, but I'll show you by means of a Venn diagram why this is true. Suppose A is the event that I'll describe it in words as if I were this sort of course in logic. Suppose A is the event I eat ice cream and B is the event I eat cake. So the inner oops, I lost out something here. So the inner portions, this, if you would read this, this says, think of complement as being negation. So this says, it is not true that I do not eat ice cream and I do not eat cake. Well, if it's not true that I do not eat ice cream or do not eat cake, that means I must eat at least one of them. Let's say that one more time, then I'll give you a pictorial proof. If it's not true, that's what this one is telling me. It's not true that I do not eat ice cream, and I do not eat cake. Well, if that's not true, then I must eat at least one of them. Okay, you can think about that, but let me show you by means of a picture. So let's suppose I want to look at this picture. Well, let's do it in pieces. Here's A, right? So A complement would be everything outside of A. B complement would be everything outside of B. So notice where what I have in common is something's wrong here. Let me get it. So A complement is everything outside A, B complement is everything outside of B. So I've given you their intersection. Why is I made a mistake here? I'm trying to figure out my mistake. What do they have in common? What they have in common, okay. What they have in common is everything outside of the loop, right? So what, this was B, by the way. So what they have in common, so here's a picture for A complement intersection B complement, is just this, right? A complement is everything outside of A. B complement is everything outside of B. So if I clean up this picture, what they have in common is just this. Now, what is the complement of this? Well, the complement of this will just be but that's equal to A union B. So again, what I did is I did this piecemeal and I put this together and I showed by a picture that A complement which one I do? A intersection B complement is equal to A union B. In the same way, you could show, I leave this as an exercise for you, is A intersection B. And these are called De Morgan's laws. I want to point out what is a complement. What's the complement of the complement?
Isn't it just A?
Yeah, the set you started with. That's correct. Okay. That means, by the way, if I wanted to, I could have written this the following way. Here's another version of De Morgan's law. And the second one would be A union B is equal to complement is equal to A complement intersection B complement. So notice distributing the complement changes union to intersection, intersection to union. In fact, more generally, if we had a whole bunch of sets, we would have A1 complement union A2 complement union A sub n complement. And similarly, if we had A1 union A2 union A sub n complemented, we get A1 intersection A2 and so on. These are sometimes useful, these laws of De Morgan. And I summarize a whole bunch of properties called the Algebra of Sets. You can find them on page 10 in the text. I could use notation that I don't really need right now, so I won't introduce it. So we have these basic notions of sets. What is I want to tell you about this? Okay. Oh yeah, I want to mention duality. It's just an interesting result. Suppose you have any statement or any theorem about a set, okay? For example, suppose I give you this set, the result, A intersection B complement union A intersection B equals A. Suppose we look at the statement. And by the way, why is this true? Let's see why this is true by means of a picture. There's A. There's B, okay? A intersection B complement is what set? It's in A and it's not in B. Right? Oh, this is A on B. I'm sorry, I forgot to put that in. By the way, notice this is the same set as A minus B, the relative complement. More than one way to represent sets. A intersection B is this piece here. When I take the union, I put them together, so I end up with A. So there's a proof by a Venn diagram. By the way, that's not a real proof, because there are lots of possibilities. Suppose A was a subset of B, or B was a subset of A, or suppose A and B were disjoint. So if you really want to give a formal proof, you have to look at all cases. I'm just looking at the more general case here. So while a Venn diagram isn't a rigorous proof, it can be made rigorous. Okay, now the principle of duality says the following. You replace union, the universe with the empty set. You replace intersection with the union, and you replace union with intersection. And if you do this, for example, suppose I did this in the example above. I would get A union B complement intersection A union B. Okay, so if I do this replacement, there was no universe or empty set. There's one more. The principle of duality says if you do this, if the first statement is a theorem, the second statement is also a theorem. And by the way, you can prove this very easily using Venn diagrams. I will leave that as an exercise to you. Okay. Now I want to talk more about Venn diagrams and how we use them and give you some examples. So let me begin with this example once again. So this is A, this is B, this is C, this will be my universal set. And let me label these as each individual region, region 1, region 2. I'm sorry, that's not region 2. I want to stick with what I have in the text. Region 2, region 3, region 4, region 5, region 6, region 7, and region 8. So I want to make sure you know how to read this. So if I want to look at region 1, notice region 1 are all elements that are in A, and they're not in B, and they're not in C. If I wanted to read region 5, those are all elements in A and C, and not in B. By the way, I would probably write this alphabetically as A intersection B complement intersection C. Maybe I should have said earlier that A intersection B, of course, is the same as B intersection A. That's sort of obvious, but I didn't say it. Similarly, A union B, the same as B union A. Look at region 4. Region 4 is, it's in A and in B and in C. What about region 8? What is that? How would I describe region 8? Well, it's not in A, and it's not in B, and it's not in C. So each of these 8 regions can be described pretty easily, I think. But you need a little bit of practice. And you'll see this is important because we're going to want to know about probabilities of events that may look like this. The probability A happens and B doesn't happen and C happens, or combinations of that type. Maybe another one here is, how about 3, region 3? Well, that's just B, right? So it's not in A, it's in B, and it's not in C. Okay. How would I indicate at least elements that are at least one of the regions? At least one of the regions means it's either in A, or in B, or in C. And by the way, oops, what happens? What is this equal to? If it's not in one of the regions, this says it's not in any of these regions. By De Morgan's law, we have this result, but notice it's obvious from my picture. If it's not in at least one of the regions, it's in none of the regions, and that's not in A, not in D, and not in C. Okay. Let me define, suppose A is a finite set. By that I mean it has it has a finite number of elements in it, okay? Then the number of elements in A is denoted by A with two absolute values around it. By the way, other books call it C of A, and sometimes that's called the cardinality of A. So this symbol just means a number of elements in A. For example, suppose A had the elements 1, 2, 3, I'm choosing one of my examples right from the text, 1, 2, 3, 5, 11, and B has 2, 5, 8, 11, 17, 11, 17, 19, and 20. Then how many elements are in A? How many different elements are in A? We just get what? 1, 2, 3, 11. That's 4. How many elements are in B? Let's count them. 1, 2, 3, 4, 5, 6, 7. Okay. What about number of elements in A intersection B? Well, A intersection B, what do they have in common? They have 2 in common and 11 in common. So the number of elements in A intersection B is 2. What about the number of elements in A union B? Well, A, got to be a little bit careful here now. What is A union B? It's 1, 2, 3, 5, 8, 11, 17, 19, 20. So what do I have? I have 1, 2, 3, 4, 5, 6, 7, 8, 9. If I didn't make a mistake just now, I got 9. Okay. So I want you to observe in this problem that the number of elements in A union B, which is 9, the number of elements in A was, what was in A? 4. And B was, what was B? B was 7. So observe the following is not true. Because we saw this is 9, and this is 4 plus 7, which is 11. So clearly that isn't true. So what would be true and why isn't it true? Anybody?
Is it because A and B are not disjoint? Like if they were disjoint, then it would be true.
That's correct. In fact, let's look at the picture. A union B would be the sum of the elements in 1 and 2, region 1 and 2 and 3. Agreed? Now notice, I have to count each one separately. But the number of elements in A consists of the regions 1 and 2. The number of elements in B consists of the regions 2 and 3. If I add these together, notice I would count the intersection twice. Everybody see that? So it's clear that what is true is the following. The number of elements in the union is equal to the number of elements in A plus the number of elements in B minus the number of elements in the intersection. This is sometimes called the addition formula. Of course, as you just mentioned a moment ago, if in fact they're disjoint, well, how many elements are in the empty set? 0, right? So then what would be true then it would be just the sum of the two because they're disjoint. But the fact that they're not disjoint gives us a little difficulty. So let me show you this can be generalized. I'll tell you how to prove it. Please don't memorize it. It's a waste of your time. I'll show you how we do problems involving it. Okay. So the natural question is, suppose we have A union B union C. We want to know how many elements are in that. Well, I'll tell you the answer and I'll tell you how to prove it. It's the number of elements in A plus the number of elements in B plus the number of elements in C minus the number of elements in A and B minus the number of elements in A and C minus the number of elements in B and C plus the number of elements in the intersection. Please don't memorize this. It's a waste of your time. I'll walk through 2 examples that'll show you how to do all these problems. By the way, sometimes the result is called the inclusion exclusion. Because notice, I'm including some sets and I'm excluding others. Now, if you wanted to prove this, here's how you would do it. Call B union C D. And now you know the formula for this, and you may apply it a couple of times. It's really easy to prove. But let me show you how you do problems like this without using either of these formulas. So 2 problems. How's my time? Oh, I'm good. They're called survey problems. So here's the first problem. Let me get my glasses on so I can read my text. I'm taking example 3 from the text, and it says the following. And then I'll do the next example, which is a little more complicated. We surveyed 80 students. 60 like math, 30 like history, 20 like both, how many like only math, B, at least one of the courses, and C, neither course. Okay. Again, you don't have to write this down. This is example number 3 on page 16 in the text. Okay. So here's what I'm going to do. I'm going to let M be the set of all students who like math. And that's an ugly circle. One more time. And I'm going to let, so this will be M. And I'll let H be the set of all students who like history. Okay, so now what we do is in this circle, I'm going to put the number of students who like it. And the trick is to work from the intersection out. So notice 20 like both. That means the number of elements in math and history which is 20. So I put a 20 here. Now I know 30 like history. Well, I know the whole circle for history must be 30. So what's left must be 10. And similarly, 60 like math. I already have 20, so I have another 40 who like math. And that accounts for 60, 70 students, right? 40 plus 20 plus 10. So what must be added to these two circles is the complement. Oh, what do I have? 60 is 30. So the number of students who like only math, meaning they like math and they don't like history, that's 40. At least one course, they like at least one, that means math or history. Well, that's just the sum of all the numbers inside the circles, which is 70. And the number that like neither of these courses, they don't like math and they don't like history. That's the complement of the 70 from the 100. I'm sorry, there are 80 students. I made a mistake. There are 80 students. So this number is wrong. Oops. Where I lost the place. Where? This number is wrong. Since there are 80 students, this is 10, correct? So this must be 10. Okay. Straightforward example. Notice I could have gotten this using the formulas. I didn't need to use a single formula here. Now let's make the problem a little more complicated. So the idea when you're doing a problem of this type is work inside out, from the intersection out. Now I could be a nasty guy, I'm not, but I could be. And I can give you the data in an order which isn't quite right in order. And you'd have to go around and work it out yourself. I'll show you what I mean by that in a minute. But let's do another problem. Let's do problem number 4.
Professor,
Yeah.
Would you tell us that there are 80 students in the survey, or would
Yes,
we-
I have to. Otherwise, we wouldn't have enough data.
Okay.
Okay, so next problem, this is example 4. We have a survey of 200 people. So I'm already telling you the number of elements in the universal set. And here's what we know. And what we do is we're looking at their driving habits, and we're looking at 3 different cars. We're looking at Audis, BMWs, and Chevrolets. Purposely A, B, and C, okay? And here's the data. 10 drive all 3. 30 drive Audis and BMWs. 50 drive only Audis. 5 drive BMWs and Chevys, but not Audis. $110 drive Audis. 25 do not drive Audis, but drive BMWs. Again, you don't need to write any of this down. It's right in the text. 40 do not drive any of these cars. Hopefully I didn't make a mistake right now. If I did, you'll find it, or I'll find it as we go along. So I'm going to let A be the set A represent all those people who drive Audis, B, all those people who drive BMWs, and C, all those people who drive Chevrolets.
Probably can you scroll up to
I'm sorry, I didn't hear that.
take notes?
You're breaking up.
He asked if you could scroll up a bit.
Can you
I didn't even hear.
slide up
I'll
the
go back to it in a second.
the last part?
And of course, I'll ask some questions here. They're right in the text, but let's get the information here. So I start with 10 drive all three. That means this has to be 10, right? The intersection of all three. $30 drive Audis and BMWs. Well, Audis and BMWs is this whole loop here, right? And what did I say? How many do that? 30? Well, I already have 10. So I need another 20. So I've filled out this group. Okay. I'm checking my books. I don't make a mistake. What's next? So I've done this one. I've done this one. 50 drive only Audis. Well, only Audis is this region here. It's out of B and out of C. And how many did I say? Did I say that was 50? So that makes this 50. Five drive BMWs and Chevrolets, but not Audis. Well, where would that be? Well, here are the people who drive BMWs and Chevrolets and not Audis. And I said that was 5. Okay. 110 drive Audis. Well, look, the only piece is this that's missing. We have 50 and 20 is 70 and 80. 80 and what make 110? What, 30? $25 do not drive Audis. So I'm out of the A circle, but drive BMWs. Well, I'm out of the A circle and B, this whole group here must be 25. I already have 5. So what's left is 20. And 40 don't drive any of these cars. Okay. So notice everything is filled except this region right here. Well, how do I find that? Well, I know in total there were how many? There were 200 people. So what do I have? I have, oops. This group alone was what, 110? I have 110 and 20 is 130. 130 and 40 is 170, 175 altogether. So if I have 175, what's missing? 25. So now I have all the information I need. So now let me see, let's look at the questions. So the questions were the following. How many people surveyed drive only Chevrolets? Well, that's the last one I just did. That's going to be 25, right? That means they don't drive Audis, they don't drive BMWs, and they drive Chevrolets. Next question. Both Audis and Chevrolets. Well, the people who drive both Audis and Chevrolets, this group right here, right? I said and, so that would be Audis and Chevrolets. That would be 40. At least one of the cars, well, we know 40 don't drive. There are 40 who don't drive any of them. So at least one of the cars is a union. The easy way is you just take 200 minus 40, which is 160, or just add up all the numbers in the inside. And the last question is exactly one car. Well, there are 50 people who drive only Audi. There are 20 people who drive only BMWs. And there are 25 people who drive only Chevrolets, which gives me 95. I get a little carried away at the end of the chapter or the end of the section in 1.2 using inclusion exclusion. I don't really need that last example there, that last problem, so I'm not going to talk about it. So let's get a little survey of what we have here. Okay, so basically I've done, I looked at basic notions of sets. Or what I like to call the algebra of sets. And that was the first section. And the second section is counting using Venn diagrams. And this is important because sometimes there are questions. I mean, a typical problem might be, if you look at the last example I just did, instead of saying how many people drove none of these cars, I could say, and actually the way I would say it on an exam would be, given this group, what's the probability that nobody drives any of these cars? So in fact, in that last example, notice there were a total of how many people? 200? There were a total of 200 people. And out of these 200 people, how many drove none of the cars? What did I get? 40? So if I ask, what's the probability that somebody drives none of the cars, without even defining probability, just from your basic understanding of what it might be, the answer would be 40 over 200 or 1/5. By the way, what you learned basically in grammar school when you first studied the basic notions of probability is really a ratio. It's the number of favorable ways an event can happen. A rough definition of a probability is the number of favorable ways an event can happen divided by the total number of ways all the events can occur. Sometimes it's written as favorable over total, F over T. For example, and we're going to give a better definition, by the way, but this is an intuitive definition. For example, if you draw, if you have a deck of cards, suppose you have 52 cards, an ordinary deck of cards, what's the probability that you draw an ace? Well, how many aces are there in the deck? 4. And there are a total of 52 cards. It would just be 1 over 13. So the point I'm trying to make is, in order to compute a probability, we have to know how to count. Now, the first examples I considered here were using Venn diagrams. Sometimes problems are more complicated, and we need more powerful ways of counting. And that's what I'm going to do next. Today's Wednesday. On Monday, what we're going to do is we're going to learn to count it a little differently using what's called permutations and combinations. And those problems can be a little bit tricky. We're not going to do really hard problems involving permutations and combinations because that'll take us too far afield. We really want to emphasize probability in this course. But we'll look at some basic ideas and how to count. And it's a different way of thinking. And I'll proceed now with the birthday problem to show you that your way of counting is pretty straightforward. By the way, I haven't been keeping track of the chats. Are there any things in the chats that you need me to address?
No, it's just answers.
Okay. Sometimes I don't notice that, so let me know. Okay, now let me just tell you the way we normally begin. If this were an in-class, I'd have people come to the board before class begins to put problems that are bothering them. What we'll do here is, if anybody has specific homework problems that are bothering them, and by the way, please do the homework on the syllabus for sections 1 and sections 2. I went through these very quickly because I had asked you a couple of weeks ago. I sent out an email telling you to read them. So please do. And I'll post sometime tonight, for those of you who didn't get the book yet, I will post tonight PDFs of sections 1 and 2. I just have to find it on my computer. And if you have any particular questions, I'll take a small sampling on Monday. And any questions that still bother you, just send me it and I'll write it up and I'll post them on Blackboard if they're very different. Okay, I'm going to stop now. I don't want to do too much the first day. I don't even know what time it is. What is it? It's 11. Oh, well, 5 minutes early. So why don't you guys do the homework? Let me stop the recording right now.